Chapter 4: Mindset and Intelligence. In decision-making, heuristic shortcuts are commonly employed for quick decisions. The availability heuristic bases decisions on easily recalled examples, though memory may not accurately reflect reality. The representativeness heuristic assesses the likelihood of an event based on its resemblance to a prototype or stereotype, potentially leading to errors like the conjunction fallacy. Understanding these problem-solving methods and decision-making heuristics empowers individuals to navigate challenges efficiently. Biases often hinder our ability to make accurate decisions, influencing our judgment in subtle yet impactful ways. Overconfidence, for instance, leads us to believe that we know more than we actually do, such as entering a test ill-prepared due to false sense of mastery gained during studying. Belief perseverance causes us to cling to our beliefs despite contradictory evidence, like disregarding unfavorable facts about a preferred political candidate during an election. Confirmation bias further exacerbates this by compelling us to seek out information that confirms our existing beliefs, ignoring dissenting viewpoints. Additionally, framing effects demonstrate how the presentation of information can skew decision-making. For instance, when presented with options for saving lives during a disease outbreak, people may think and make different choices based on how the options are framed. Highlighting the same outcome in different ways can lead to contrasting decisions. In problem solving, our minds rely on semantic networks to assess how stored information is. These networks organize concepts in interconnected webs, akin to how data might be structured in a computer. Initially, semantic networks were believed to follow a hierarchical model, with broader categories leading to more specific ones. However, subsequent research suggests that semantic networks are more fluid and individualized, shaped by personal experiences and knowledge. The concept of spreading activation illustrates how activating one concept can trigger the retrieval of related concepts. This phenomenon explains instances of failed memories or recalling incorrect yet closely associated information. By understanding these cognitive processes, we can better navigate decision-making and problem-solving tasks, mitigating the impact of biases on our choices. Intelligence encompasses a mental capacity allowing individuals to learn from experiences, tackle problems, and apply knowledge to adapt to new situations. Traditionally, intelligence has been quantified through numerical scores, measuring aptitude across various tasks and comparing performance to others. One prevalent theory posits the existence of a singular general intelligence factor, supported by the observation that individuals excelling in one cognitive domain often perform well in others, indicating a common underlying ability. Alternatively, some theories propose multiple intelligences, including analytical/academic, creative, known as novel idea generation and adaptation, and practical, solving real-world problems. While IQ tests primarily measure analytical intelligence, other frameworks like emotional intelligence emphasize perceiving, understanding, and managing emotions in social interactions. Another perspective divides intelligence into fluid and crystallized categories. Fluid intelligence pertains to abstract reasoning, which declines with age, while crystallized intelligence involves accumulated knowledge and verbal proficiency, typically increasing or remaining stable into adulthood. The nature versus nurture debate surrounding intelligence explores the balance between genetic inheritance and environmental influences. Studies examining correlations among twins raised in varying environments reveal a blend of genetic and environmental factors shaping intelligence. While there's no definitive reason for fostering genius, certain environments can hinder intellectual development. Several theories attempt to explain the concept of intelligence. Spearman's general intelligence Spearman proposed the existence of a single factor known as the G factor, which accounts for an individual's overall intellectual performance across various cognitive tasks. According to this theory, intelligence is a singular general ability underlying all cognitive functions. And then there's Gardner's theory of multiple intelligences. Gardner's theory diverges from Spearman's by positing the existence of multiple intelligences, each representing different modalities of intelligence. Gardner identified 8 distinct intelligences, including linguistic, logical, mathematical, spatial, musical, bodily, kinesthetic, interpersonal, intrapersonal, and naturalistic intelligences, suggesting that individuals may excel in one or more of these domains. Galton's theory of hereditary genius proposes that human ability and intelligence are primarily determined by hereditary factors. He believed that intellectual prowess, like other traits, is passed down through generations, emphasizing the role of genetics in shaping intelligence. Binet's concept of mental age introduces the concept of mental age, which compares a child's intellectual performance to the average intellectual ability expected for their chronological age. This concept serves as the basis for the development of intelligence tests, with the goal of identifying children who may require additional educational support. Individual mindsets also play a role in intelligence perception. Those with a fixed mindset believe intelligence is innate and unchangeable, while those embracing a growth mindset view intelligence as malleable through learning and effort, often achieving more as a result. Understanding how language intertwines with cognition provides multifaceted insights into the intricate ways in which our thoughts form and our minds evolve. From diverse angles, theories of language and cognition illuminate the profound impact language exerts on our thinking processes and developmental trajectories. Behavioralists, aligning with empiricism, view language merely as conditioned behavior. In contrast, nativists, following rationalism, argue for language's innate nature. Materialists focus on the neurological processes underlying language use, while interactionists stress the interplay between innate biology and environmental cues. The debate over linguistic relativity questions whether language influences thought. Universalism contends that thought entirely determines language, while Piaget posited that language emerges once children develop certain cognitive abilities. Vygotsky's view sits between Piaget and universalism, suggesting that language and thought initially develop independently but converge over time, eventually being used simultaneously. Linguistic determinism explores the influence of language on thought, with weak hypotheses suggesting language shapes cognition to some extent, while strong hypotheses, like the Sapir-Whorfian hypothesis, argue that language fundamentally structures cognitive processes. For example, the Hopi tribe, language lacking grammatical tense, reportedly affects their conceptualization of time. In the realm of language development, nativist theories, championed by Noam Chomsky, propose an innate language acquisition device, facilitating language learning, with a critical period for language acquisition occurring in early childhood. In contrast, learning theories, epitomized by Skinner, posit language acquisition as a result of operant conditioning. Interactionists, influenced by Vygotsky, emphasize the interaction between biological and social factors in language acquisition, highlighting the role of social interaction and motivation in learning language. Overall, these theories offer distinct insights into the complex relationship between language and cognition, shaping our understanding of how language influences thought and development. Language processing in the brain is predominantly localized in the left hemisphere for about 90% of people. Two key areas involved in language functions are Broca's area, responsible for speech production, and Wernicke's area, responsible for language comprehension. Damage to Broca's area results in expressive aphasia, where individuals struggle to produce speech but retain comprehension. Conversely, damage to Wernicke's area leads to receptive aphasia, characterized by nonsensical speech production and impaired understanding of language. The connection between Broca's and Wernicke's area is facilitated by the arcuate fasciculosus, a bundle of nerves crucial for language processing. When this pathway is damaged, individuals may experience conduction aphasia, disrupting the transmission between listening and speaking. Other language-related impairments, such as agraphia, which is the inability to write, and anomia, which is the ability to name things, can also occur. Language processing in the brain illustrates how complex tasks are divided into smaller components distributed across various brain regions. This organization allows for resilience in the face of localized damage, as other parts of the brain can adapt and compensate for deficits through neural plasticity. For example, individuals who experience a stroke affecting language areas may gradually regain speech abilities through therapy as other brain regions take on speech-related functions. However, disrupting communication between the brain hemispheres, such as by severing the corpus callosum, can lead to unique challenges. Split brain patients resulting from the surgery exhibit impairment communications between the hemispheres, affecting language and other cognitive functions. For example, the left hemisphere, responsible for language, cannot communicate with the right hemisphere, which handles aspects like action, perception, and attention. This disconnection can manifest as difficulties in naming objects presented in the left visual field, highlighting the specialization of each hemisphere and the intricate interplay between language and the perception in the brain. The limbic system plays a central role in processing emotions and memories, comprising key structures like the hypothalamus, amygdala, thalamus, and hippocampus. Serving as a control center for basic emotions and drives, this system orchestrates a storage and retrieval of emotionally linked memories. A helpful mnemonic, Hippo wears a hat, can aid in remembering its components, the hypothalamus, the hippocampus, amygdala, and thalamus. The thalamus acts as a sensory relay station, directing sensory inputs to appropriate areas in the cortex. Notably, the sense of smell bypass the thalamus, directly connecting to areas closer to the amygdala, underscoring the intimate link between emotions and sensory experiences. The amygdala, often dubbed the aggression center, influences emotional responses, such as anger, violence, fear, and anxiety. Stimulation of the amygdala can elicit aggressive or fearful behaviors, while damage to it may induce a mellowing effect, or conditions like Kluver-Bucy syndrome, characterized by disinhibited behavior. The hippocampus plays a crucial role in forming new memories, converting short-term memories into long-term ones. Damage to the hippocampus may impair the ability to create new memories while leaving existing ones intact. Additionally, the hypothalamus, nestled below the thalamus, regulates the autonomic nervous system, influencing responses like fight or flight versus rest and digest, and controls the endocrine system. The cerebral hemispheres and prefrontal cortex further shape emotional experiences and regulation. Research suggests that positive emotions are associated with increased activity in the left hemisphere, while negative emotions exhibited heightened activity in the right hemisphere. Functional divisions within the prefrontal cortex govern higher order functions, including executive control, problem solving, decision making, and social behavior. Phineas Gage was a railroad construction foreman in the 19th century who experienced a traumatic accident in 1848. While he was working, a large iron rod accidentally shot through his skull, piercing his frontal lobe. Remarkably, Gage survived the injury, but his personality and behavior underwent significant changes. Before the accident, Gage was described as responsible, reliable, and hardworking. However, after the injury, he became impulsive, unreliable, and prone to mood swings. This dramatic shift in his behavior provided an early evidence of the critical role of the prefrontal cortex in regulating personality and social conduct. Gage's case has since been iconic in the field of neuroscience, contributing to our understanding of brain functions and the localization of specific cognitive abilities within the brain. The autonomic nervous system governs physiological changes that occur involuntarily in response to emotions, consisting of two branches: the sympathetic nervous system, responsible for fight or flight, and the parasympathetic nervous system, which promotes rest and digest. Sympathetic activation leads to pupil dilation, increased heart rate and respiration, decreased salivation, and heightened glucose release and adrenaline levels, while parasympathetic activation causes pupil constriction, lowered heart and respiratory rates, increased glucose storage, and enhanced digestion. Emotions encompass subjective experiences accompanied by physiological, cognitive, and behavioral changes, all interconnected. Physiological components include changes like increased heart rate or muscle tension, while cognitive components involve mental assessments and interpretations of situations. Behavioral components manifest as actions influenced by emotion, which can be temporary, varying in intensity, and involuntary. Paul Ekman identified 6 universal emotions: happiness, sadness, fear, disgust, anger, and surprise, recognized across cultures, suggesting an innate understanding of emotions for survival, as proposed by Darwin. Contempt has also been added as a 7th universal emotion. Theories of emotion examine the interplay between physiological, cognitive, and behavioral responses. The James Lange theory posits that emotions stem from the perception of physiological responses, suggesting that we feel emotions based on our bodily reactions. In contrast, the Cannon-Bard theory asserts that physiological responses and emotions occur simultaneously. The Schechter-Singer theory emphasizes the simultaneous role in physiological and cognitive processes in forming emotions, with the interpretation of arousal influencing emotional experiences. Lazarus' theory further highlights the importance of cognitive appraisal in shaping emotional responses, suggesting that the way we interpret situations influences our behavior and emotional experiences. Additionally, the Yerkes-Dodson law suggests that optimal performance occurs when individuals experiencing moderate emotional arousal, with extreme emotional states impairing performance. This underscores the intricate relationship between emotions, physiological responses, cognitive processes, and behavioral outcomes in shaping human experiences and behaviors. Thank you guys so much for listening to Chapter 4. We'll go into Chapter 5 for the next episode, but if you guys liked the video, please give it a like, comment, subscribe. Thanks again for watching. Have a great day.